Welcome to this presentation on effective record length. My name is David Margo, and I'm a lead civil engineer with the Risk Management Center. This presentation has three primary objectives. The first is that you will be able to give a correct definition for effective record length. The second is that you will be able to summarize why we need effective record length. And the third is that you will be able to describe how effective record length is estimated. In this presentation, we'll cover the following topics. We'll start off with a review of some uncertainty concepts. We'll follow that up with the definition of effective record length. Then we'll demonstrate how effective record length can be used. And finally, we'll show you how to calculate an effective record length estimate. When it comes to uncertainty, there are two general types. The first is natural variability, which is due to randomness. It is usually assumed to be irreducible, and it answers questions such as, will a major flood happen sometime this year? The two frequency curves plotted at the bottom of the slide show differences in natural variability, which generally come from the values of the distribution parameters. So in the plot on the left, we can see that the range of flows between an AEP of 0.5 and an AEP of 0.001 is about 5,900 CFS. In the plot on the right, for the same range of AEP, we see a much larger range of possible flow values. This reflects more natural variability, and it comes from the fact that the standard deviation is higher and the skew is higher in the plot on the right compared to the plot on the left. The second general type of uncertainty is knowledge uncertainty, which refers to uncertainty due to a lack of data. Of course, this uncertainty can be reduced with more data and further study. It answers questions like, if a 500-year flood were to occur, how big would that flood be? The two plots shown on the slide show differences in knowledge uncertainty. The plot on the left, at the 100-year flood or the 0.01 annual exceedance probability, has a 90% confidence interval that spans a range of about 7,000 CFS for a record length of about 100 years of data. In the plot on the right, we see a much wider 90% confidence interval at the 100-year flood event due to the shorter record length of only 50 years. This reflects more knowledge uncertainty. So the bottom line is that the record length is generally an indication of the amount of knowledge uncertainty, with a longer record length resulting in a smaller amount of knowledge uncertainty. So in addition to the confidence intervals, the knowledge uncertainty also affects the expected or the mean hazard curve. So in the two plots shown is a comparison of two mean hazard curves with different amounts of knowledge uncertainty. So in the plot on the left, we have a longer record length of 100 years that results in a less frequent mean hazard curve. In the plot on the right, we have the same computed parameters, but a different mean hazard curve because of the shorter record length of only 50 years, making the mean hazard more frequent. Another important concept when thinking about effective record length is quantile variance. Quantile variance is a measure of the uncertainty in the flow at a given annual exceedance probability. It's related to the confidence intervals. Quantile essentially means a non-exceedance probability, or 1 minus the annual exceedance probability. And remember, the variance is a measure of the dispersion or the uncertainty in the flow estimate at a given AEP. So in the two plots, we can see how we get from confidence intervals to quantile variance and how they're related. So the plot on the left shows a frequency curve with several different confidence limits plotted. From the confidence limits, we can generate the distribution of flow at that AEP value, which is the plot on the right. From that probability distribution that represents the uncertainty in the flow estimate at that AEP value, we can estimate the variance, which is essentially a measure of the dispersion or the width of that distribution. The value of the quantile variance depends on both the natural variability and the knowledge uncertainty. In this example, we can see that an increase in the standard deviation or the skew parameter increases the natural variability, which will also increase the value of the quantile variance. So in the plot on the right, which has a higher standard deviation and a higher skew, we get a higher value for quantile variance compared to the plot shown on the left. In this example, we can see how the quantile variance also depends on the knowledge uncertainty, which is represented by the record length. So in this example, we can see that an increase in the record length reduces the knowledge uncertainty, which also reduces the quantile variance. So the plot on the right, which has twice the record length as the plot on the left, will have a smaller quantile variance. Now that we've reviewed some uncertainty concepts, let's dive into record length and effective record length. When all of the data consists of known values or systematic data, the record length is simply equal to the number of data. Each data value contains 1 year of information in the record. So what do we do when we have a data set with censored data that consists of perception thresholds and flow intervals? How many years of information is provided by this data set? Initially, we really don't know because each year of censored data contains less than 1 year of information, but we don't know exactly how much. Data values with larger uncertainty will generally contain less information, and values with smaller uncertainty will generally contain more information. So what is effective record length, and what does it really mean? In our data set on the left, we have censored data consisting of perception thresholds and flow intervals, so we don't know the actual record length. But we can try to find an equivalent record of systematic data that will be equivalent to our data set. There are 2 criteria that need to be met for these 2 data sets to be considered equivalent. The first is that the computed curves must be the same. In other words, the natural variability must be the same. And second, the uncertainty must be the same, which means that the knowledge uncertainty must also be the same. So in the data set on the right, which has 162 years of systematic data, we get the same computed curve and the same uncertainty bounds, which means that this data set is equivalent to our data set, which is the data set shown on the left. So this means that 162 years is the effective record length for our data set that consists of the censored data with perception thresholds and flow intervals. Why do we need an effective record length, and what do we use it for? In the plot on the left, we start with a frequency curve that we've computed from our data that includes some censored data. We now need to model that frequency curve in our flood hazard or our risk model. The inputs to most of these types of models consists of 2 things: the distribution parameters that define the frequency curve and the effective record length that define the uncertainty in the frequency curve. So we need both in order to run our flood hazard model or our risk model. And this includes many of the common models in use today, such as HEC FDA and the flood risk compute option in HEC Watt. We can use a convenient property of the quantile variance to help us estimate an effective record length. In this plot, we can see that the inverse of the quantile variance, which is the y-axis value, has a linear relationship with the record length. This is true for many of the commonly used distributions in hydrology, such as the normal distribution, the log normal distribution, the log Pearson type 3 distribution, and the generalized extreme value distribution. Here is how we can use the linear relationship between the inverse of quantile variance and the record length to get an estimate of the effective record length. We start with the frequency analysis of our data set and get an estimate of the quantile variance at a particular annual exceedance probability. Software like HEC SSP will calculate and report this value for you as shown in the figure on the left-hand side. We can then estimate points on either side of our data set using systematic data. So in this example, on the right-hand side, we assume a systematic data set of 81 years, which is equal to the number of systematic data in our data set. We assume it has the same parameters, the same mean, standard deviation, and skew as our computed frequency curve. And we run that through an analysis to get the quantile variance. The inverse quantile variance for that point is 23.4. We then do the same thing for another systematic data set that has 840 years of record, which is equal to our total historic period for our data set. Again, we run that through an analysis to get the quantile variance, and the inverse of the quantile variance is equal to 221.2 for this example. Knowing that the relationship between these 3 points should be linear, we can now do a simple linear interpolation calculation to get the effective record length for our data value, which has an inverse quantile variance of 44.6. And when we do that interpolation, we get an effective record length estimate of 162 years. To wrap up this presentation on effective record length, I want to share a few key things. First is that most of the current software out there in use does not currently calculate and report an effective record length based on censored data, although this is being worked on and you will see it in future versions of the software. There are also some unofficial spreadsheet tools that are available throughout the core, but you should use these with caution and at your own risk because they have not been fully verified or documented. And lastly, as a default, you can always use a trial and error method to match the uncertainty from your frequency curve to the uncertainty that is being computed in your flood hazard or your risk model. This concludes the presentation. Thank you for your time and for your attention.